you want to perform a Newton-Raphson-like way of optimizing the likelihood or the log likelihood, then that is a pretty tricky operation, because you are making small little steps according to the direction along which the function will increase the most. And such an algorithm is generally very much sensitive to the choice of the initial value. So if you choose the initial value really close to the final optimizer, then you have good chance of converging to it. But if you start far away, you might not converge, or you might converge to some local maximum. So it is very important that you choose your initial value carefully. Now for that, we use a variant of this GLS technique, which is sort of very insensitive to the initial value. So you start from anything, and then this technique, which itself is an iterative one, the technique that I am going to describe now, will take you to more or less close to the correct value. After that, you will run your Newton-Raphson-like thing, the gradient-based thing, from that value to get to the final value. So the thing that I am going to discuss occurs in the first step of any Newton-Raphson-like technique. Now for this technique, we start with y equal to x beta plus epsilon, where epsilon has mean 0 and variance given by some particular structure. Now we assume that we have two things. Number one, we assume, so these are computational assumptions on basically the structure of capital sigma, this function. One, we can find Cholesky decomposition or some such square root decomposition analytically. So this is available. You really do not have to carry out any numerical technique to do this thing. Just looking at the structure, we can immediately say what is going to be the Cholesky decomposition. For example, if it is just a diagonal matrix, the Cholesky square root will be just taking square root of the diagonal entries. Now for all the techniques that you have learned, compound symmetry and then autoregressive one, etc., you can analytically compute such a square root. And the second thing is, if I give you some data, if I give you epsilon vector, something which has this, if I give you this, if is given, of course in practice it is not given, you are not observing epsilon, but if I give you a vector, then you can estimate theta. Then can estimate theta. So if these two assumptions are met, then there is a very simple way by which you can try to estimate this beta. And this technique that we are going to learn is called iteratedly reweighted least squares. Iteratively, repeatedly, reweighted least squares. And the technique goes like this. You first start with a guess for theta. So step 0. In step 0, you start with a guess. And this guess turns out to be quite unimportant. So you can just start with something which I call theta 0. Start with. So this algorithm is pretty insensitive with respect to the choice of this, with some theta 0, some initial guess. So once you have that, you compute the Cholesky square root using this technique and you apply GLS. So now that you know theta naught, so you just assume that theta is known at this value. So now it is of the form. So typically we will assume it like this. So I will call it like this: epsilon is sigma square times some r. So r is the correlation matrix. So sigma square is unknown. So capital sigma theta I am taking of the form, this form, where I will possibly say this above r. That is a better way. Then can estimate sigma Right, so then you can estimate theta, so that is okay. So start with some this, and once you have this, now you are in a position where you can apply GLS. So step 1, apply GLS. And when you apply GLS, you will need to compute the Cholesky square root or some square root of R, which is analytically available. So you just put theta naught here, and that does it. Once you have that, you get some estimate of beta hat. So to get beta naught hat, whatever you get, plug that to get your epsilon hat. Step 3, define epsilon hat 1 as y minus x beta hat naught. So now you get some estimate of some proxy values for epsilons. So I have assumed that if epsilons are given, then I can find out my theta. So you have applied GLS to get this as well as your sigma hat, sigma square hat. From GLS you can get that also. So now you go into step 4, which is basically you now get theta 1 hat. So use 2 to get theta hat, the next value, theta hat 1. So I will put there a 0 also. So now you get these values. And with this, you get back to step 1. So with this new value, you again apply GLS, and you keep on doing this until you converge. So you keep on doing this until convergence. Is there any guarantee that it is going to converge? No, not always, but generally, if you do this, say, some large number of times, not very large number of times, even 20, 30 steps, you will see that you at least come more or less close to a very meaningful value of this theta, and from that point onwards, you start your more rigorous Newton-Raphson method type of thing. And then the final thing converges. So whenever you are asking the computer to find out the MLE of beta and theta, what it will do is that it will start with some crude initial estimates, and then initial estimate of theta, and then it will apply this for some 20 steps. Whatever it gets, it fits there as the initial value in the Newton-Raphson type iteration, which is much more sensitive to the initial value, and report the final convergence value. So, iteratively reweighted least squares, you understand why it is called iteratively reweighted, because I am using GLS every time, but I am changing that particular matrix, because first I am working with R theta naught, then R theta 1, etc., etc. So I am iteratively reweighting it, and this is an important algorithm which generally sits inside your software. You do not have to do it, but something that we can understand easily.